My problem says, consider the function f of x, which is equal to e to the power of x plus m times x for various fixed values of m. And then there's stuff to do. So I think it's sort of, when it says fixed values of m, it's saying that m's a specific number. I just happen to not know what it is, but it stays the same when I'm trying to figure out what this function is. Okay, so I could think about different values of m and see what it does. So if m is 0, I just get e to the x, which I know looks something like that, because it's plus 0x. And if m is 1, or just some positive number, that's like y equals mx. And then when you add e to the x, it'll add this onto there, so everything will get higher by this amount. So it'll be quite close to it here, and then you'll be adding 1 to it, and then it'll get up really fast. So if I just make this a dotted line, that's e to the x plus mx. But if m's a negative number, I should make that a dotted line. Then it'll do down like that, and e to the x is still 1 there, and it will get closer and closer to that because it's really small over this side. And then it'll go up this way, and I reckon e to the x grows faster than any polynomial. So as fast as this goes down, e to the x is going to go up faster than it. So eventually I think it's going to go up like that. Okay, so I reckon this is what's going to look like. So it's going to be sort of increasing for these ones, and there's going to be a turning point for these ones. But I don't really know. There might be a place where somewhere in between here and here that it is the place where it starts being ones with turning points. Okay. All right, part A, show that this function is always concave up for any value of m. Well, they all do look concave up, so that seems to work fine for me. This is still concave up, even though it doesn't come back up again. So I guess concave up would go with the second derivative. If the second derivative is positive, then it's definitely concave up on that zone. So I need to find the second derivative. So f of x is e to the power of x plus m times x. And the derivative of that, the derivative of e to the power of x is just e to the power of x again. And the derivative of m times x is the number m that's attached to x. So doesn't really matter what the number is, it'll always work that way. And then f double dashed, the derivative of e to the x is still e to the x, and the derivative of a constant is 0. And so I just get that. And e to the power of x is never negative, it's always positive. So since the second derivative is always positive, it must always be concave up. Okay, that's what I would write if I was handing this in to someone. Okay. Now, what was the next question? B, for which values of m does the function have a turning point? Well, to have a turning point, it would have to be decreasing on one side and increasing on the other, or possibly increasing on one side and decreasing on the other. And at a turning point, the first derivative is usually 0. So at a turning point, f dashed x is 0, and f dashed x was e to the power of x plus m. So that would be 0. And so e to the power of x would have to be minus m. And so, all right, well, that's only going to have a solution if m is negative, because minus m, e to the power of x can't be negative. Now, e to the power of x is definitely positive. So minus m is positive. So therefore m has to be less than 0. Okay, and let me just see if it works. And then when I do ln on both sides, ln of e to the x will be x. Okay, and that's okay. It looks bad because ln is not usually supposed to do work on a negative number, but that's not a negative number because m is already negative. Okay. So cool, and that will exist, definitely. And let me just check. Is it really going to be a turning point? Yes, it is, because it's concave up everywhere. And if you've got a place where the first derivative is 0 and it's concave up at that spot, it's definitely a turning point. Okay, so there's a turning point at x equals ln minus m for m negative. Okay, and part C, since it's concave up, this turning point is a local minimum, because concave up means it goes up this way, so it has to be a minimum, just like the drawing I made said. Okay, cool. I just want to check this in a computer for drawing the graph to see if it's matching what I thought it should do. This is GeoGebra, and I'm going to say f of x equals e to the power of x plus m times x, and it's made a guess that I think m should be a variable that we get to change. So if I change m up here, it does get steeper and steeper, and then when m is 0, that's the graph I drew, and then when it's negative, there's a turning point. And let me just mark the point ln of minus m, because that was the x coordinate, and f of ln of minus m. Oh, looks like a turning point. Yeah. Yes, it really is a turning point, no matter what. Cool. Well, that's very exciting. Okay, so we know the second derivative is always positive. We've found when it has a turning point, and the fact that it's a local minimum whenever it does have one.